he will tell us about domino tilings in dimension-free. Nicolau.
Okay. Well, thanks everybody for being here. We usually begin by thanking the organizers, but I want to thank especially Ricardo for doing such a good job here. And I've, of course, well, probably everybody here knows that I collaborated with Carlos for ages now. We were computing right now with Marx. I'm not even sure he's here. But do you remember how long we have been sharing the present office, Carlos?
No.
Since 2001, 2002. So that makes it 23, 24 years. And we first met, when I was a student here, I heard stories about Carlos, but Carlos was away doing his PhD and postdoc. So we first met briefly when I was on vacation from my PhD. And he was professor here. But more significantly, since '89, when I returned from my PhD and he returned from his postdoc, and we started collaborating immediately. And there are many, many subjects about which Carlos and I collaborated. I had to choose one here. And I chose one about which we collaborated very early. You can, if you pay, well, that is me, of course, and Carlos is here, among many other people. This is a subject we collaborated very early on, that I didn't know, but Carlos had been working on this problem of domino tilings with undergraduates. And one of them, by the way, I knew very well already. And so he asked me a question, and we went on and did one of my first major papers. This one of the results I'm going to show you here. And I continued working on this, not always together with Carlos, because our interests sometimes took us in slightly different directions. And you're going to see that it's very different from most of the other talks you've seen, but it's all work in collaboration with Carlos. So it goes to show the breadth of his interests. Okay, so happy birthday. So we're going to talk about domino tilings. If you paid attention to the title, it said in dimension 3, but we begin here, the talk, in dimension 2, which is much more studied and much more understood, and it's also where we started. So a domino, we're not going to play the game of dominoes. We just use it as tiles, okay? So a domino is this 2x1 blue rectangle here is a domino. So we're going to fill in a board with these tiles. So a box, okay, some people consider a different point of view of filling the entire plane, and then you have this infinite, uncountable set of tilings of the entire plane. That's not the main point of view here. The main point of view here is much more elementary. You fix a box here, and then you fill it with little pieces like this. Okay? So what are interesting questions here? So if it is a domino, a 2D domino, for now in the first 15 minutes or so it's going to be 2D. It's a rectangular tile, sides 1 and 2. So we start with a quadriculated region here. Questions which people have investigated. I'm not going to be as systematic with citing related research here because there's too much material the way it is already. Okay, so sorry for the many people who did very interesting work related to this, which I'm going to speak, to skip, not going to speak about. So one question is, okay, you're given a region here, how do you decide, well, here obviously you have a tiling, but in general, how do you decide whether a tiling exists or not? Or how do you count tilings? Given a region, is there some interesting, informative, clever way of counting how many tilings you have? Or maybe we want to classify tilings. This is a less precise question, but it's a very important question. For some regions, you draw a random tiling and you see patterns there, which has led to very important investigation. But what we're going to focus on is this last question here. So we want to study the connectivity of the space of all tilings of a prescribed region by flips. So I have to explain what this means. So this is a flip. You take two pieces, two dominoes, you remove them from the board, rotate 90 degrees and place them back. Okay? It's the only move you can do which involves only two dominoes, only non-trivial move, which we can do, moving only two dominoes. Okay? So that's a flip. So given two tilings of the same region, so this is like a puzzle, right? You have this configuration here and you want to arrive at this other configuration and you want to do flip-flip. How can you tell whether or not it's possible or not possible? So here is an example. You consider this square with a hole, okay? There's a hole in the middle of the region. And you have two tilings here. This one, here in the middle, it seems to be stuck. You cannot perform flips right away. But it's not clear how this information is helpful because there is plenty of dominoes here which are not stuck. So when you start making moves there, maybe you can set these interior dominoes free and not immediately clear whether they are equivalent or not. Well, they are not. There exists an invariant which says they are not equivalent, which works like this. You draw a cut here. You orient your drawings. I hope you can see there are little arrows here inside these dominoes pointing from the magenta square to the white square. Yes? Okay? And you can do that, and then you have these little arrows in the dominoes, here and also here. And you count the way they cross the cut with sign. Okay? So here you have one domino crossing this way from left to right. Here also one domino, but from right to left. So that would be +1 and -1. And the remark here is that when you perform a flip, this flux does not change. Because you could flip maybe these two guys here, and then you would have, instead of 0 2, or maybe instead of 1, 3, but the signs of the new crossings cancel out. So it doesn't change. So no, the answer is no. They are not equivalent. Okay? So, this is Carlos. And these are the two, they were undergraduate students under Carlos Tomei, and they were working on this problem. And so when Carlos asked, I was aware of Thurston's work. So we put the ingredients together and we proved the theorem, which extends Thurston's result to a more general setting. And this was one nice paper. So if you have a planar region, two tilings can be joined if and only if they have the same flux. Yeah. So if the flux is different, you clearly cannot join them. But if you have the same flux, then yes, you can join them. And what Thurston did was consider simply connected regions. And then it's always true, you can always join two tilings because there is no flux. Okay? So we extended that result using this concept of height function. The concept of height function had to be adapted to generalize it to this other situation. And by the way, this concept was based on actually more complicated problems. This is one of the many situations in math where the first contribution is not necessarily the simplest one. The problem which Conway and Lagares were studying was harder than this. Okay. So let's go to 3D. Here is a picture of a box full of 3D dominoes. Do you understand that picture? Well, if you do, you're blessed with X-ray vision and 3D understanding, because this is very quickly becomes incomprehensible what this picture is trying to show, because the dominoes are standing one in front of the other. So that's not a good way to draw this. Draw it like that, it works much better. So we imagine that the box is here, and we are describing it layer by layer. Or perhaps you can imagine that it's like describing a building, where you say the first floor is like this, and then you draw the first floor, draw the second floor, and so on. Okay? So this domino here, or these domino here, they are contained on the first floor, and that's why you see them completely contained on the first floor. But this and this gray square together with this white square, they are a vertical domino in the sense that half of it is on the first floor, half of it is on the second floor. Okay? So I told you at the beginning, dominoes in dimension 3 are much less studied and much less understood than dominoes in dimension 2. And why is that? Because everything is much harder. But this is, of course, not a formal mathematical statement. But as far as an informal statement can be clearly true, that is clearly true. Because every question you ask, it's true. If you ask about counting tilings, it's much harder. If you ask about classifying tilings, much harder. Everything seems to be much harder. For instance, we didn't show how to count tilings, but in dimension 2, This was solved by Castelline, Temple, Fisher sometime in the 60s. There's a very clever way to count domino tilings of a planar region. Okay? And in dimension 3, it's an open problem. But these are crude estimates for which there are easy proofs, and much more is known about this than this, but it's still a significant window. Apparently there is a conjecture of what is the correct move, but it's only a conjecture. How about deciding whether the 3D region is stylable? That's another problem. Okay, it's also hard, and this one is provably hard. Well, in dimension 2, this was also addressed by Thurston, and it's easy. There is a quick algorithm, very quick algorithm. You study the region and you say, yes, here, and not only there exists a tiling, but here is a tiling. Or no, not only there is no tiling, but here is a proof of why exactly there is no tiling. In dimension 3, no such luck. Igor PUC and his collaborators, they have many results showing that it's complicated and hard in formal senses, right? NP complete or something like that. And how about flips? What can we say about flips in dimension 3? Well, what is a flip, first of all? A flip, I think the definition is so natural, it's unavoidable, really. A flip is the same thing it was in dimension 2. You take two pieces and put them back after rotating 90 degrees. Maybe in this plane, maybe in this plane. So here in the drawing, this is a 4 by 4 by 3 box, and we observe these two red dominoes here, and we say, I can perform a flip here. And then you arrive here at these two dominoes here. And now you perform a blue flip. That's why this domino here, if you pay attention, it's magenta because it's red, both red and blue. So you take these two dominoes here and perform a flip. But this should be light blue here to indicate that we did a flip in a different direction. And this illustrates that flips can interfere with one another. Of course they can. So is it possible to join any two tilings by flips? Well, let's give some notation. We say they're equivalent if there exists. A sequence here means, of course, a finite sequence, right? A finite sequence of flips, taking one tiling to another tiling. So when is it true? Can we prove something similar to theorem A? Well, that's a vague question, yeah. Well, what is similar? Well, maybe if we are elastic about the concept of what is similar, maybe we can prove something. But is it always possible? This is a clear mathematical question here, unlike the previous one. Is it always possible to join two tilings by a sequence of flips? This is emphatically no. No, it's not true. And it's not true. So there's a quick way to prove that it's not true is to say, hey, look at this tiling here of this 3 by 3 by 2 box. Here is a tiling of the 3 by 3 by 2 box. It admits no flips. It's stuck. And there are obviously many other tilings of this little box, so it's not connected by flips. Okay? Well, when you see this explanation, say, well, okay, maybe this is because this is a very special, very small box. Maybe this doesn't really count. No. There is a larger example here, and an even larger example here, and when you look at this example a little bit, you can see, you can generalize to very large boxes. You have examples of tilings which are completely stuck. No flip at all. Okay. These examples seem to be extremely rare, by the way. If you do randomly select tilings, you do not arrive at tilings which are completely stuck. These examples were done by hand, not by randomly searching for something. Okay, so maybe if they are rare, maybe the situation is this. And this is a reaction I get a lot from combinatorics, and my collaborators also get from combinatorics also. Oh, okay, so maybe there is a giant component. Yeah, we've seen giant components in many problems. Sure, but it's like that. There are these very special tilings which admit no flips, or maybe a tiny component of, there's one flip which you can do and nothing else. And then there is a giant component. Is it like that? Maybe. Well, no. But in order to show why it's no, let me first go in a slightly different direction. Let's introduce another local move, a trit. It's a local move involving 3 dominoes, 1, 2, 3, in different directions. We remove them and we put them back. Okay? This is the only move involving 3 dominoes which does not immediately reduce to a very few flips. Okay, so it's not arbitrary. Here is another picture of a trit. Okay? Yes? So, open question. First, a remark. If you look at a small but not too small box, 4 by 4 by 4, any 2 tilings can be joined by flips or trits. This can be verified by brute force. We will look at this example more carefully in a couple of slides. But is this true for larger boxes? Yeah, but this seems to be a hard problem. Yeah, we don't know. We don't know whether it's true or not. It's known to be false if instead of a box, you look at regions with different shapes. But the counterexamples are regions which are very special in one way or another. For example, there exist cylinders. Is it clear what a cylinder means? A cylinder means you draw some planar region here and then do Cartesian product by an interval. Yes? So it's like a cylinder, except that here it's not a circle, obviously, it's some other shape. Draw some examples, yes?
What is very thin?
Very thin. Oh, do we have chalk? This. So you can say, well, you're kidding me, right? But this is too thin. There's no room for a thread here. So how can you expect it to be connected by flips and threads if you give an example which is so thin that there's no room for a thread? Okay, so it's debatable whether this counterexample is really relevant here because it's so extreme, so degenerate. And for other regions which are not extremely thin in that way, but then they are not cylinders. So maybe they are also special in some other point of view. So it's not clear. We don't know. Open question. But well, let me say a few things we do know. Okay? We do know that this is, I should be citing this is not our result. This is by someone else. I should have written the name here, and now I don't remember. But, sorry. It's known that you can always perform either a flip or a thread. So you do not have completely isolated tilings where you can perform no flip, no thread. For the region I drew, yes, there is. For that very strange example. And also for this one here, which I did not draw. But here, no. Here, this does not happen. If we refine, I will explain more carefully what is a refinement in a few minutes, but I think you can imagine what it is. You take each cube and cut it like it's a piece of tofu. You cut it into smaller cubes. Yes? Then it's true. Then it's true, then you can join it by flips and threads. Okay. If we allow a little extra space, and sorry, I don't know exactly what a little means. It looks like a little means very, very little. But the proof doesn't give an explicit estimate of what is little space. So you have a box, and you say, oh, let's say I introduce maybe two floors here, two new floors. They begin arranged with all dominoes, maybe vertical, and I can borrow space from these two extra floors, provided I return it in perfect order at the end of the procedure. Then it's true. Except that maybe it's not two floors, maybe it's 1 million floors. We don't know. Okay, so I mentioned the refinement about cutting tofu and stuff. Well, what is a refinement? You take each unit cube and cut it into 5 by 5 by 5 small cubes. Yes? Clear? And each domino is also cut into 5 by 5 by 5 smaller dominoes in the same direction. And then it's true, and you may be asking yourself, well, why 5 here? I will not explain carefully why 5, but I can give a quick explanation. 2 would ruin the problem, because it would completely negate the difference between black and white cubes. So it would completely destroy the theory. 3 would work, but it would confuse the authors. And we don't want that, okay? It would confuse the authors because you get confused when you're painting little cubes when you divide it 3 by 3. Because you don't, if you start with a big white cube and you cut it like this, how are you going to use information that the big cube was white? Is it for the majority of small cubes or for the central cube, because it gives two different answers. So it's confusing. So let's not do that. Because 5 is 1 mod 4, so it works. It's not so confusing as 3. Okay. So, but what's this question? When are two tilings connected by flips? And I said, oh, there are some examples which are stuck, and I promised the more conceptual answer. And the conceptual answer is by introducing an invariant. The twist is an invariant. So for each tiling you have an integer, which is a twist. And when you perform flips, it does not change. And when you perform trits, it does change. It goes up by 1 or down by 1. So I'm going to give several explanations of what a twist is, but first let me give you properties which characterize a twist if you're willing to believe in the consistency of what I'm saying. Okay? So it does not change when you perform a flip. When you perform a trit, you add 1 or subtract 1, and that depends on orientation. Okay? Because you have these dominoes here, you do this right-hand thing, and you see is it positive or negative, and that's a sign. And also it remains the same when a refinement is performed, and the fact is, here, the fact is that this characterizes what a twist is. It's not at all obvious. It's a theorem, right? But it's true. It characterizes what a twist is, up to additive constant, of course. But maybe if you're bold, there is a definition for the cylinder. It's short, it's elementary, and it's very opaque. You read it and you don't understand what is it we're talking about here. Well, you can't win every time, right? Okay. So you count pairs of reverse dominoes, one aligned with the x-axis, the one aligned with the y-axis, and they are reverse, and one is above the other, like this. Yes? This one is in direction, the x, y, z, okay? One is in the direction of the x-axis, one is in the direction of the y-axis, and one is partly above the other one. You count these pairs with sign, add everything up, divide by 4. Yeah, that's a twist. Very weird. Yeah, but there, you have a definition. Okay. So, given these properties, if you believe them, if they are connected, the twist is equal. But it's not if and only if. The twist can be equal and not imply that you can join by flips. There are many examples. There are some examples where one of the tilings is stuck. And you say, oh, that's why it's stuck. But here it's special, but in a subtler way. It's special because it has only 2 floors. And 2 is a very small number. There are special things happening here. Okay? So it's also special. Maybe it doesn't count either. But you can verify that it's not equivalent. And these two are stuck. These two are tilings of the 4x4x4 box. If you compute the twist, it's 0 in both cases, and they're both completely stuck. So, no, they don't join. Here are, by the way, some examples of tilings of twist. +2, +1, 0, -1 and -2 for the 4x4x2 box. So you can see that these are, no, this is one of the examples in the previous slide. And notice that reflection changes the sign because reflection changes orientation over 3. Yeah, that makes sense. But rotation does not change orientation, so it's the same twist. By the way, if the region is, this is for boxes, okay, the definition. If the region is not contractible, not a box, maybe it has a hole, maybe it's like this kind of cheese which has bubbles in it. Then maybe the twist does not take values in the integers, it takes values in the integers mod something. So I'll try again to explain what a twist is. This is an explanation of recent work with Boris Gezin. So you take each domino and you construct, it's a definition using water going through pipes. So maybe it sounds a little bit like some of the talks we've been hearing. In each domino you construct 5 pipes like this. The square here shows where the 5 pipes cross the central square here. And if you notice, there are pipes going out here, 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 and coming in here, here, here. So when you put the dominoes together, the pipes fit. And then you can turn on the water, and it will work. Construct these pipes, turn on the water. And this defines what's called a divergence-free vector field. The kind of vector field which describes water moving, especially if it's moving inside pipes. Okay? This is the situation where these concepts of helicity and relative helicity are defined, and it's a twist. Yeah, the twist is a relative helicity of the vector field. Okay. This is yet another explanation of what is a twist, but I think this is getting too long. I'll skip this. If you have a bigger cycle, what happens to the twist? You construct, but this is more complicated, but you construct a Seifert surface for your longer cycle. You measure the flux of the domino tiling through your Seifert surface, and that gives you the difference of twist between one tiling and the other tiling. Okay?
In the previous example, what was the, I mean, I could see the pipes, but what's the definition of the twist?
Here?
Yeah.
The slide is referring you to the concept of helicity of divergence-free vector field. I can write a formula of helicity if you want to. You take the vector field, you take the curl inverse of the vector field, because it has 0 divergence, so it's a curl of someone. You take the product of that and integrate. Yeah? Arnold and Kezin and other people have written a lot about this, and I met with Boris Kezin and I said, yeah, I'm working on this problem in combinatorics and I think it's related to your stuff. So yeah, it is. Yeah, but I couldn't really go into all these main explanations. So this is really just to show that it's complicated, yeah. So this is another explanation. You take a long cycle, you construct a Seifert surface, measure the flow, and that's the difference between the two twists. Yeah? I don't think there exists a definition. We saw one definition, at least for cylinders. We saw one definition which was short, elementary, and opaque, very opaque. Yeah? Now, here are other definitions which are not elementary. They are clear if you understand other stuff. But I don't think there exists a definition. This is, of course, not a mathematical statement. But I don't think there exists a definition which is simultaneously short, reasonably short, elementary, and very clear and intuitive. I think you're asking for too much if you want all these together. So I'm doing my best here to communicate what the twist is. Oh, let's look at an example. Maybe you'll believe more if you see an example. Let's look at a 4x4x4 box. People sometimes are very surprised by such a small little box, and all we're doing is filling it with dominoes. How many ways can you do that? More than 5 billion. Wow, okay, that's a large number. Well, the number of, it's not hard, we skip this completely. But I mentioned that the number of tilings of a region, it grows exponentially with the volume of the region. So yeah, you get big numbers. You're going to see much larger numbers in another slide. And if you look at the connected components via flips, you have 93 components. The largest one has 4.4 billion, and this is, by the way, one place where an audience with many people in combinatorics, they say, ha, giant component. And then we say, no, wrong. You think it's a giant component because these numbers, you think they are nearby, they are not nearby. You're being fooled because the box is too small, it's too special. But these numbers are large, but you should look at these numbers. We'll see, but we'll talk more about the distribution in a second. So the largest component has this. This is about 10 times smaller. Components number, we call this component number 0. Components number 1 and 2 have this number of tilings, 310 million. And then it goes down up to tiny components which have only one flip. We'll state theorems in a minute. Here is a diagram of these three components here take most of the tilings. But the correct way to see a giant component here is to see it's a giant component once you take into account the twist. Okay? And twist is in this vertical axis here. So this is twist 0, twist 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4. And now if you look at all tilings of twist 0, then this is a real giant component. It has almost everything, because you see that is the largest one. The next one with twist 0 has 280,000. Oh, okay, that's a big difference. Yeah. And if you look at tilings with twist 1. Where is the next one? Oh, it's here. 236 tilings, but that's a big difference, yeah. Okay. So, given these distributions, we can say that most tilings with a prescribed twist are in the giant component. So that in a sense say that twist is only significant if invariant, okay? Significant because we have to rule out cheating, like saying the invariant is a number of the tiling representative of the connected component. But that's cheating. That's not a significant invariant. So in a sense, yes. So is it true that, except for a few special cases, if you have the same twist, this implies that they're joined by flips? And here is yes. Meaning, yes, if you allow me to state the theorem in exactly the way I know how to prove it, but there are open questions here. So is it true that they usually can be joined by flips? And in some cases, with suitable hypothesis, yes, but there are open problems here. So for large boxes, the twist appears to follow normal distribution. And here is the distribution of the twist in this box here, 4 by 4 by 110. Now, that's a larger box. And by the way, the number of tilings here, the 6 means 6 times 10 to the 314. Okay. Is it true? Oh, but that's a theorem. If we fix a basis and let the height go to infinity, then it follows a normal distribution. We can say its average is 0. We can say what the variant is. We can say everything you want about it, but only in this very special situation. If you look at a cubical box, we would like to know we don't know. Okay? So we know many things, but there are many open questions also. How much time do I have?
5 minutes.
5 minutes, okay. So let me show you a few numbers and a few. So here is, for the 4 by 4 by 8 box, we can compute the number of tilings with each prescribed value of the twist. And you see this looks like a parabola here. The physical curve, when you look at the size of the decimal expansion of the numbers, it does this. What is this curve? It's a parabola. That's a normal distribution. Yeah? Because the size of number on paper is a log of the number. Yes? But it's true. I mean, but it's not just a remark made by looking at huge numbers printed on a screen. It's a theorem. These are numbers for 4 by 4 by 12. These are exact numbers, by the way. We know how to compute them for boxes of the form 4 by 4 by n, but we do not know, I don't think anyone knows how to count tilings for the 6 by 6 by 6 box. Okay? Okay, let's skip over this. Let me just state a few theorems here and finish. Okay. So assume you're looking at cylinders like this, and the basis is a rectangle. Okay? And assume it's not too small. So if you look at the numbers L1 and L2, they are both at least 3. Okay. 2 and 3 are special. 1 and 2 are special. So okay, that's a reasonable hypothesis. Then it's true the following, but if they have the same twist, then they're equivalent once you put a little extra room. But that's the result I already announced. If you have two tilings here in a box, I just hadn't stated it that carefully. If you have tilings in a box and they have the same twist, they can be joined, provided I have a little room, a little extra room to maneuver my pieces. This M here, M is how much extra room do you need? It's not 0, because we're talking about joining by flips only, okay? For the 4x4x4 box, M equal 2 works. But here, there is an extra variable here. We're not just the two horizontal dimensions, but also the vertical dimension N here. So we don't know for 4x4 what it is. But it looks like it's 2. My bet would be it's also 2. So with a little extra room, it's already true. That equal twist means you can join one to the other. Okay, so the probability that you have the same twist and they are not equivalent, this probability goes to 0, and it goes to 0 very quickly. It grows to 0 exponentially fast. Very unlikely. Very unlikely to have two tilings which have the same twist, but they are not equivalent. If the minimum is 2, it's a completely different situation, by the way. It's an opposite situation, really. It's given that the twist is equal, the probability that they are equivalent goes to 0 very quickly. Okay? Rafael Maheiros, who just finished his PhD with this part of his thesis. And I want to quickly show more joint work with students. So we investigated not dominoes, but slabs. The slab is, as I mentioned, 2x2x1. What can we say about tilings of boxes by slabs? So here is a, can you see this? It's a little small, but I hope you can see. Here is a box of size 6 by 6 by 12. And it's full of slabs. We're drawing it also floor by floor. And is it equivalent to flips to a horizontal tiling? How would we know that? Hard problem. Yeah, no, it's not, because we can adapt the twist. And this is very cute construction. Good place to end the talk. Paint the cubes with 4 colors, not black and white, 4 colors, red, yellow, green, and blue, like that. Okay? So 2 adjacent cubes always have different colors, and 2 cubes which are adjacent by an edge also have different colors. Only cubes which are adjacent by a vertex have the same color. Paint it like that. Choose 2 colors, say red and green. Inflate the red and the green. Deflate the yellow and the blue. What happens? Your slab tiling becomes a domino tiling. Now compute the twist. The twist is invariant. Okay. Thank you.
Are there questions for the group?
Yes.
What was the original motivation to, because you are, among many things, you are a combinatorial person, but you are the originator of the whole gang?
No. But there were many other people studying domino tilings before I entered this. In fact, Thurston was studying it before that was my introduction to the subject, was Thurston. And Carlos was independently studying it. But before these people, we have these results by Castelline, Temperley, and Fisher. These are results from the 60s, when I was being born. And Castelline is a physicist, well, was a physicist. So from physical motivations, I didn't mention them because I feel a little embarrassed just to say, physics like this problem, and I have no idea exactly why. Well, I have a vague idea of why they're interested in it, but I still feel a little, well, it depends on the audience, the context. I may mention it or not mention it, but it is relevant to physics in a way which I'm not qualified to explain.
Let me take the liberty just to add one question of someone that is completely, this is a sort of conservative game. Can you, the fluids, Boris Kazin is a conservative guy.
Yes.
If you put compressibility as an analog, can you make like a hole and try to see if the tides can be kind of go to a black hole and disappear and then?
Yeah. We do have. Well, it's conservative to a point. I didn't tell the story of the fluid in all its glory. Let me go back to. Here, there's water coming from nowhere here, arriving from God knows where, and going out here and going God knows where. Okay, that's not quite a conservative vector field yet. So what we have to do is we have this region where we put these pipes, and then you have to construct a protective shell which has its own pipes, which will solve the difficulty we just mentioned. But this water here, it should go somewhere, and maybe it will come back here, or here, I don't know, somewhere else. So you have to construct this shell. And the way, you must have noticed that almost all definitions of twist are defined up to an additive constant. Yeah, and this additive constant depends on what exactly you do on this protective shell, which is a little arbitrary. What is it exactly you're going to do? In some cases, you can exploit symmetry and say, no, it's natural. Yes, it's natural, because respecting this symmetry, it makes no difference. But in general, if the region doesn't have some special symmetry, this additive constant is arbitrary. And here, what is tricky is the definition of twist, because you are no longer in a contractible region. You are in a region with a hole. So it has non-trivial homotopy. So that's tricky.
So is there any, in 3 dimensions, is there any analog of the height function, which is more local?
Yes, but it's a complicated object and it's not clear to what an extent it's helpful. What you do is this, you draw little arrows inside each domino. But all you do is maybe you already saw the 5-pipe construction, right? You like the 5-pipe construction. I sense you liked it. Yeah, here. Yeah? The equivalent of a height function is curl inverse of this vector field. Yeah? But it's a complicated object. It's not as helpful as a height function. Or at least we mathematicians have not been clever enough to use it to obtain as many results as have been obtained with height functions. But maybe it's just that we haven't tried enough, we're not clever enough, maybe, but it seems that it's a more complicated object.
Thank you.
Okay, thank you.